So we'll now talk about decorators. And decorators are, in my mind, one of the neatest features of Python. What do decorators do? Well, they add functionalities to existing functions. And most importantly, they do so without interfering with the body of the function. So imagine you have some function that you're programming that does some math. And you decide suddenly that you want to log what's happening, or maybe to cache what's happening, or maybe to profile what's happening. You don't want to introduce that code within the body of the function because potentially you will mess up with your computation. So Python offers a neat way to do this, to add the functionality without messing with the body of the function. And it gets even better because very often, actually, people want to add logging or caching or profiling. So there exists a bank of decorators that you can use to add all those functionalities to existing functions. And the point is you only need to implement that once. Now, those get quite complicated. They are implemented, you can use them, but they are quite complicated. So instead of starting with the hard example, I'll start with the naive example that we build by hand and then refine it a little bit, and then finally tell you where you can actually find the more advanced examples. So in order to do this, I'll run Python on the decorator file. And because I want to mark quite a few stopping points, I have implemented a little function pause that will ask for my input. So it will ask me to press the return key. So let's run Python decorator.py. So what does this do? Well, you see that square of 9 is printed, and this is coming from here. And then I will call the function square logged of 9 that has all this output, basically. And then I pause, and that's where I am now. So what is square logged of 9? Well, square logged is kind of like the function square, so it takes n and returns n squared, except that we have applied to that function square another function called naive logging. So naive logging is this guy here. It's a naive implementation of a decorator that implements a logging functionality. So how does that work? Well, here, naive logging took as an argument square. So in general, it takes as argument a function, and I've called this func. So whenever you see func, you could think square. So how does it work? Well, within the body of naive logging, it will define a new function, and this function is here. And it's called I don't want to see this because you are not supposed to see this. It's just a temporary function. And this takes positional and keyword arguments, and doesn't matter what. It's just the general set of arguments a function can take. And it contains just two statements. The second one is that it should return the result of applying func to these arguments. So basically, the behavior of I don't want to see this is essentially the same as the behavior of func, except that there is an extra statement, which is a printing statement. Whenever you call I don't want to see this, you will print this line, but where the arguments that are passed to this string to format this string are the name of func, so square, for instance, and the arguments that are received. So let's see that. When I ask square logged 9, I really execute square of 9 eventually, but at some point I'll also execute a print statement telling me what arguments I've called that square with. And this is what you see here. You see that I've called square with arguments 9 and an empty dictionary. And this is a tuple with just one entry. Okay, so this was for square logged. So we're all the way to here, and we can go there. Okay, but the advantage is that once you have defined naive logging, then you're good to go. You've defined it once in your life, and then you can reuse it for any function you want to log. For instance, the factorial. So let's go all the way to the next pause, and let's see what happens. So now I have factorial 4, and then I print factorial 4, and I compute factorial of n using the regular technique. But I've decided to decorate factorial with this decorator naive logging. So this at naive logging does exactly factorial equals naive logging of factorial. So let me just type that for a second. So you see it automatically does that. Naive logging. Okay, so because it recognizes that very often you don't want to define a new name for the function because you're logging it, just simply because you're logging it. This add allows you not to change the function name, but to still decorate that function with this extra functionality. So this means that outside of the function, you don't need to know that you have wrapped. You can still use factorial. And if naive logging is well written, that won't interfere with the execution of the rest of the program. Okay, so what did this call to factorial 4 return? Well, it says here that I called factorial with arguments 4, and then arguments 3, and then arguments 2, and then arguments 1. And this is exactly the behavior I would expect. All right, so this was for logging. And now we want to talk about caching. So to talk about caching, I need to tell you a little bit about what caching is. But maybe I'll take one specific example of caching that you know about, and this is in web browsers. So if you are using your web browser, you have a cache associated to that web browser. So if you go to a website, your browser will save a whole bunch of data about the website and will save that in its cache. So that when you go again to the website later, it won't have to reload a whole bunch of data. It will still have some of the data locally. This can be a problem if the website changes, then you have to completely reload to do a hard reload of the page. So it's going to be the same idea here. If we have a function that we want to compute, we compute it once, we compute it twice, and if we expect the result not to change from one to the other, we can just cache the result. We can just save the result and later on look it up rather than reapplying the function, which might be expensive. So I'll go to the next pause, and the next pause just involves this code. So maybe I shouldn't have put that code over there. Let's just look at this one for the moment. So no caching Fibonacci of n is just a regular implementation of Fibonacci. So it calls it itself at n-2 and n-1. And just to tell you what's going on, I've decided to log what's going on with naive logging. So let's print no caching Fibonacci of 4. So if you want to think, you should pause a little bit now and think hard about what will be printed here. So let's see it. So when I do no caching Fibonacci 4, first I call no caching Fibonacci with argument 4, and then 2, and then 0. And this results from digging here into this one again and again. And then I go back out, and I'm still computing no caching Fibonacci of 2. I've just computed no caching Fibonacci of 0 here, so now I need to compute no caching Fibonacci of 1. And this is where you see that. So now I've computed no caching Fibonacci of 2. I need to compute it for 3. And then and so on and so on. You can follow the whole thing. You see that there are several calls to no caching Fibonacci at the same arguments, which is a bit stupid, because if you have computed once, you should be able to compute it again. So instead, we'll now use another decorator called naive caching, the one I defined up there, and I don't want to explain just for the moment. And we define the same implementation of Fibonacci, which uses Fibonacci at n-2 and Fibonacci at n-1. And again, we print Fibonacci of 4. And so what will be the result? You see that now I've only done 5 calls, for Fibonacci. I've called it at 4, which resulted in me calling it at 2, which resulted in me calling it at 0, and then back to 2, and this forces me to compute it at 1. And then I still have to compute it at 3, so I compute at 3, but this will require me to compute it at 1. And I already know the value at 1. So I've gone through exactly the same things here, except that now I don't have to compute anything else. I can just look up in my table that I am compiling in the back. So how am I compiling this table? I'm doing it with naive caching. So naive caching applied to a function, what does it do? Well, it will create first a cache, so a dictionary. And then we'll define a new function. And again, I call it, I don't want to see this because it's not relevant. And we'll take some arguments. And if the arguments is in the cache, it just simply returns the cached value for that key. Otherwise, it does compute the value of the function at those arguments, and then it saves that value into the cache, and it returns the value. The point is that for a second call, I won't need to go through the else part. I can just pick it out in the first part. So if your function is expensive to compute, You just compute it once at every argument where it's called, and then you save it. So that's a tremendous gain in some really recursive formulas. So for instance, the balance parenthesis you could do easily with naive caching, and you could do it much better. So you could still use the recursive construction, which is kind of expensive, but with the naive caching, it's greatly improved. So I had paused here, and just before pausing, I printed 2 lines. And this was Fibonacci name, which asked me for the name of the function Fibonacci, and Fibonacci doc, which asked me for the documentation of Fibonacci. So I would expect Fibonacci name to be Fibonacci and Fibonacci doc to be this part. This would all be true if I hadn't wrapped with some naive decorators. So let's see what happens. Well, the Fibonacci name is I don't want to see this, and the Fibonacci doc is this is only a temporary function, so this documentation shouldn't really show, right? So what is happening is that you actually see the name of this function and the documentation of this function. This is because that's really the function I'm returning here, right? I'm really returning that guy, which has that doc and that name. That's not what I want, really. I want my Fibonacci to be wrapped, but wrapped in such a way that it still has its name and it still has its doc. So how can I do this? Well, you can essentially do the same thing again at a higher level. So we had defined here 2 decorators, naive caching and naive logging. Well, how did we do this? We defined some functions, right? We defined naive logging and naive caching here. So what is missing, one way to do it, is to add a decorator at the moment where you define those decorators themselves. So you want to add a decorator saying, hey, what I'm about to define is a decorator, so please do your magic so things happen fine. And this is what this does. So this guy here is a decorator of decorators. So when I do later on a definition of smarter logging, this is essentially the same definition as the naive logging above, except that when I define it, I use @simple decorator here. And same thing with, so then I can call smarter factorial and with the smarter logging, and you will see that things are better. So actually, you won't see it for this one, but I can also do smarter caching with the simple decorator. And then I can take smarter Fibonacci, use smarter logging and smarter caching, and then I can print Fibonacci of 4 and print smarter Fibonacci of 4. So all this will have exactly the same behavior as before. The difference will be here that I will have retained everything about the Fibonacci. So let's see this when I press enter. So actually you could see it. I've called smarter factorial with a pause. So if I do this, you see that I have computed the smarter factorial. Okay, that's fine. And then if I press enter again, I compute now smarter Fibonacci, but I can ask for smarter Fibonacci's name, and this will be smarter Fibonacci. It won't be I don't want to see this. And Fibonacci doc will be computes the Fibonacci sequence. It won't be this is a temporary function, so this documentation shouldn't really show. Okay, so this was all done through this decorator, simple decorator, and I didn't tell you what that does, so let's go back. So simple decorator takes as argument a function that I'll call decorator, and will return eventually another function called new decorator. So it's this function new decorator, well, it's a decorator, so it takes as argument a function f, and so on and so on. So you can trace down everything that's happening. But you see that essentially it's doing what we were doing before. It's applying the decorator to f, so logging to square, for instance, or caching to Fibonacci. But it's also retaining the names and the doc and the dictionaries associated to the objects. So we haven't really seen that yet, but it's carrying over all the internal data that Python keeps track of. So that later on you have an object new decorator that is very well hiding the fact that it's decorating a function, because whenever you ask for its internals, it just returns the internals of the original decorator. Okay, So this was for decorators. I understand this is a quick introduction to them, but they are very useful, and you actually don't really need to know how to implement one. You just need to know a good set of decorators, or you need to know how to Google them, how to find them, and then that's what I do usually. You just copy paste the code, and then you start decorating all the functions that are relevant to you with the appropriate names. So you can see some documentation also about functools.wrap, so the function wrap in the package in the module functools, and this does essentially what simple decorator does, but it's a less naive implementation, a faster implementation. So that's another option for you.